In the vast expanse of our solar system, Venus stands out, not just for its scorching temperatures or crushing atmosphere, but for its alien terrain that harbors geological wonders we're only beginning to decipher. A planet shrouded in dense clouds and cloaked in mystery, Venus challenges the boundaries of planetary science. And now, a peculiar formation on its volcanic plains has become the latest puzzle for geologists. Massive, perfectly rounded, flat-topped structures that some have dubbed pancake domes. Scattered across the Venusian landscape, these pancake domes stretch wide, up to 90 miles across, but remain curiously shallow, usually under 1 mile in height. To the untrained eye, they resemble dropped dollops of syrup on a griddle, frozen in time. But these are no whimsical shapes. They are geological artifacts that hint at processes far more violent and complex than anything found in a kitchen. They're unlike anything we see on Earth or the Moon, with their striking symmetry and sheer size suggesting a formation process unique to Venus. Many of them are found clustered around coronae, vast circular features that hint at mantle plumes pushing up through the crust. In some cases, multiple pancake domes overlap like stacked records, suggesting sequential eruptions. Their uniformity is astounding, yet they show no central vent or summit crater, traits common in most Earth volcanoes. This absence raises the question, are these even volcanoes in the traditional sense? The mystery of the pancake domes dates back to the early 1990s, when NASA's Magellan spacecraft, equipped with a powerful radar system, pierced Venus's opaque clouds and revealed its surface in extraordinary detail. Among the thousands of volcanic features it documented, these domes immediately stood out. At the time, researchers could only hypothesize their origins. Were they shield volcanoes? Lava lakes? Giant blisters from underground explosions? With limited data, speculation ran wild. Magellan's mission reshaped our understanding of Venus. It showed us a world without plate tectonics, where heat builds up and escapes through massive resurfacing events. It painted Venus as a planet that had possibly erased most of its geological history in one dramatic moment, possibly within the last several 100 million years. Pancake domes, then, might be among the first geological features to reappear after that planetary reset. In May of 2025, a study published in the Journal of Geophysical Research, Planets offered a breakthrough. Led by Madison Borelli, a postdoctoral researcher at the Georgia Institute of Technology, and co-authored by Paul Byrne, a planetary scientist at Washington University in St. Louis, the study took a fresh approach. Using computer simulations and data from Magellan, the team focused on a particularly striking dome named Narina Tholus, an 88.5-mile-wide volcanic structure located along the eastern edge of the Aramaiti corona, a circular tectonic feature that spans over 200 miles. The study didn't just examine surface features. It interrogated the physical behavior of Venus's crust. Could it flex like rubber? Was it brittle like glass? Or somewhere in between? These questions held the key to understanding how something so vast could stay so flat. The researchers developed sophisticated 3D models that mimicked how lava might flow across different types of crust, both rigid and flexible. By adjusting the crustal properties in their simulations and experimenting with lavas of various viscosities and densities, they began to understand how the pancake domes could have formed. The results were telling. When viscous, ultra-dense lava was allowed to flow over a weak or flexing crust, the crust would sag slightly under the enormous weight. This sagging created a shallow depression surrounded by a subtle rim, effectively forming a containment bowl that helped the lava pool into a large, flat disk. This insight was crucial. On a rigid crust, the lava spread more erratically and failed to produce the flat-topped, uniform structures seen on Venus. But with a yielding surface, the lava formed domes nearly identical to the real thing. The key the team found was in the properties of the lava. It had to be incredibly dense, over 2,400 kilograms per cubic meter, and incredibly thick, more than 1 trillion times more viscous than water. That's over 100 times thicker than peanut butter, and a staggering figure even by planetary standards. The team concluded that such lava likely cooled very slowly, taking hundreds of thousands of Earth years to solidify fully. And in that time, the surrounding crust may have adjusted, continuing to deform under the pressure. This interplay between lava and crust likely sculpted the striking pancake-like shapes we now observe. This suggests that Venus's magmatic systems might be driven by slow, sustained upwellings rather than sudden explosive events. These pancake domes are lava's quiet but monumental expression, a slow-motion exhale of the planet's inner heat. On Earth, lava this viscous is exceedingly rare. It's usually associated with silica-rich rhyolite magma, which is often explosive due to gas buildup. But Venus, with its crushing atmospheric pressure, about 90 times that of Earth, can suppress explosive eruptions. That means thick, slow-moving lava could have flowed more gently, spreading outward instead of bursting upward. The dense, dome-shaped features thus suggest a radically different style of volcanism from what we're used to. These domes are not merely volcanic leftovers, they're fingerprints of a planet behaving in a way we're just starting to comprehend. These flows also suggest a surprising consistency in Venus's internal chemistry, raising the possibility that the planet has maintained stable mantle conditions for far longer than Earth. While our planet has fractured, subducted, and recycled its crust for billions of years, Venus may have pursued a more stagnant but persistent geological path. The flexible crust is another revelation. It implies that Venus's outer shell is not entirely solidified or static. Instead, it may be in motion, shifting, bending, and reacting to the forces below. This adds new weight to the theory that Venus could still be geologically active today. In fact, other studies in recent years have hinted at current volcanic activity and crustal deformation. Taken together, these findings challenge the long-held belief that Venus is a geologically dead world. The pancake domes may be more than relics, they might be part of an ongoing planetary story. The prospect of modern volcanic activity on Venus is electrifying. It means we could one day witness eruptions, or at least the heat signatures of fresh flows, erupting in real time through new missions. If these domes are still forming, they are writing Venus's history not in stone, but in molten rock. Interestingly, the study also hints at the possibility that water may once have played a role in Venus's volcanic history. On Earth, water in magma can significantly lower viscosity and influence eruption style. If Venus once had surface or subsurface water, perhaps billions of years ago, it could have affected the chemical makeup of the lava, influencing how these domes formed. While there's no direct evidence yet for ancient Venusian oceans, features like pancake domes push us to re-examine that question with fresh eyes. It also invites comparison to early Earth. Could Venus be showing us what our planet might have looked like in its earliest eons, before plate tectonics and oceans reshaped everything? In a way, Venus may be a time capsule of a lost terrestrial chapter. Fortunately, we may not have to wait long for more answers. NASA's upcoming Veritas mission, scheduled for the late 2020s, will map the surface of Venus in unprecedented detail using advanced radar and infrared tools. Its partner mission, Da Vinci, will plunge through the atmosphere, analyzing its chemistry to uncover its secrets. These missions could verify whether pancake domes are widespread or localized. They may even detect active geological changes, seismic tremors, thermal anomalies, or fresh lava flows, offering a real-time look at Venus's restless heart. ESA's Envision orbiter, set to launch in the early 2030s, will complement this work by peering deeper into Venus's subsurface and helping us understand how the planet's interior behaves today. Venus is revealing itself not as a static wasteland, but as a planet that has breathed, flexed, and perhaps even erupted in the geologically recent past. Its pancake domes are more than visual curiosities. They are geological signatures of immense forces and ancient flows. Each one tells a story written in molten rock and planetary tension, a story still unfolding under dense clouds and crushing heat. We're on the edge of a Venusian renaissance, with new missions poised to illuminate what lies within its cloudy shroud. And with every pancake dome we study, we edge closer to understanding the strange rhythms of this mysterious sister world. If you want to stay updated on the most incredible planetary discoveries and learn how Venus might reshape how we think about planetary evolution, make sure to subscribe. The universe is only getting stranger, and you won't want to miss what's coming next.